Hey everybody, thank you for being here today. My name's Logan. Today I'm going to be presenting our work titled Energy Optimal Motion Planning for Agents, Barycentric Motion, and Collision Avoidance Constraints. So here's just a brief outline of what I'm going to be talking about today. I'm going to introduce the problem, talk about some related literature, and then we really have two parts to our result. The first one is our main sort of theoretical result, and the second part is applying this to our particular type of constraint in a system we're trying to optimize. And then finally, we'll quickly do some conclusions and discuss future work. So really what we're trying to do with this work is do optimal planning, so optimal trajectory generation. And so this consists of a number of steps. First, you're going to generate your boundary conditions, where you start, where you end. After that, you're going to calculate an unconstrained solution that connects your initial and final states together. And then you're going to determine if any constraints have been violated. If they haven't, you're done. But a lot of the time, because we're doing constraint control, the unconstrained solution will not be feasible. In this case, what you're going to do is figure out which constraint you're violating. You might be going above the maximum speed, above the maximum control effort. You may be overlapping with an obstacle. And so what you do is you're going to sort of piece in a little bit of constrained trajectory. So for example, if you're a vehicle and your unconstrained trajectory violates the speed limit, you'll travel unconstrained for a while. At some point, you're going to travel at a speed equal to the speed limit, and then you'll exit back to an unconstrained trajectory and reach your final location, final state. And this has to be, optimally pieced together. We have a system of algebraic equations to determine the state and time that you enter and exit. And once you've done this, you then check again, are any other constraints violated? If not, you're done. If they are, you piece in another constraint corresponding to the one that was violated. You solve a bigger system of algebraic equations until you eventually have your feasible trajectory. So we try to calculate these sort of optimal motion primitives offline. V equals V max, U equals U min. What do you do when a constraint's active? And since we have these already, really the hardest part of this process is step 4, actually piecing them together. So that's the problem that we're trying to, improve and make easier with this work. And there's definitely a lot of literature in this sort of constrained optimal control area. On the top, we have a couple of recent papers that are looking at connected and automated vehicles and interacting with rear-end safety constraints while you're driving down a road. On the bottom is also some recent work in constraint-driven control, where the agents are just energy minimizers and they actually behave because constraints are imposed on them. So, and this is just a very brief snapshot of some of the work that's going on here. So for our general result, here's the setup. We're going to have an agent that has k states, and each state is going to occupy some, subset of Rn. And we're going to have integrator dynamics. So we'll start with our control input, and we can integrate all the way up to get to our position. So we've got this k integrator. And we also are going to have an energy model where our energy consumption is proportional to the L2 norm of the control input. Again, this is mostly, we use this for planning purposes. So this is a decent energy surrogate. And even in some vehicles, you may find this to be a useful energy model to minimize transient operation. And finally, of course, we need to have some constraints. So here we have this function g. It's a function of the state. It's a function of time. It can also be a function of the control input, although that's sort of a trivial case for the approach we're about to show you. And we require g to be a class c cubed minus 1 function. So the idea here is we need to be able to take q derivatives of g, where q is the minimum number of derivatives required so that any part of the control input explicitly appears in the function g. And this is very standard for what we're doing in optimal control. This is not at all sort of a ridiculous thing to ask for. So in this context, we've got these k integrator dynamics. We've got the L2 norm of control effort as our energy cost. We've got a scalar constraint that's a function of our state. At this point, we're going to look at when we transition between an unconstrained and a constrained trajectory. We pass through whatever the optimal state and time is, and we switch. Or we exit from a constrained back to unconstrained. And really the assumption we need here is that the constraint needs to be active for some non-zero interval of time. So this can't be like an interior point constraint. We need to remain on this constrained arc. And if this is the case, it pretty much just falls out of the equations, the optimality equations, that the control input must be continuous when we make this transition. So I'll just briefly go over sort of the proof of this. We're going to start with the Hamiltonian jump condition. This is just rewritten in the same sort of notation and stuff that Bryson and Ho use in the optimal control book. You can see we've got the the L2 norm of the control input, our integrand here, plus being the time instant just after transitioning, and minus being the time instant just before. We also have these lambdas. These are our co-states or our covectors or our influence functions, whatever you'd like to call them. And then we have F. These are our integrator dynamics. And on the right-hand side here, we've got this pi transpose. This is just a vector of constants. And we have this n subscript t. N is the vector of tangency conditions. So we're taking these q derivatives, and we're using the last one to generate what the control input looks like when the constraint is active. And so we take the q minus 1 derivatives of g and g itself, and we just stack them up and put them in n. So n contains g, g dot, g double dot, all the way to the q minus 1th derivative. And then the subscript t is just the partial derivative with respect to time. And so we have a handful of other sort of optimality conditions as well, and we can substitute them into this equation and rearrange, and we get this here on the bottom, where now on the left hand, we have a bunch of basically dot products of the control input before and after the transition, and on the right, we have a function of pi, n, our tangency equations, and then also the dynamics. And it's pretty straightforward to show that on the left-hand side, if the control input is continuous, so u plus equals u minus, you get that the left-hand side must be equal to 0. And it's if and only if. So if the left-hand side is equal to 0, then we can really say the right-hand side being equal to 0 is kind of an equivalent condition for the u's to be continuous. And we don't know what these pi's are. We know they're generally non-zero. So we're just looking at everything that's left multiplied by pi. And so we end up with this equation. We have the partial derivative of our tangency conditions with respect to time, plus the partial derivative of our tangency conditions with respect to the state, times our dynamics is 0. This is our equivalent condition that if it holds, the control input must be continuous. And sort of the last step here is to just look at each row of this equation, right? So the first row is going to be g itself. So that's r equals 0 here. We have partial g partial t plus partial g partial x dx dt. And this is for every single row, right? The g itself, first derivative, second derivative, third derivative, all with respect to time. And this is actually exactly equal to the full derivative of g, right? Which, because we have this non-zero interval of time, must also be equal to 0. So, just by our premise of the derivatives of g existing, we know that the control input must be continuous at this junction between the unconstrained and constrained arcs. So we have a quick motivating example also to show why we might want to apply this, or some of the ways it's useful. So here, consider an agent in R2. We've got double integrator dynamics, so we're controlling acceleration directly. And we're also going to have this time varying reference position, P sub R. Now this could easily be extended to a multi-agent case where maybe you have one point you want all the agents to go to, so PR is shared, or you have a formation and you have several different PRs, one for each agent, and you're trying to push them out into a formation. And sort of inspired by this paper, Fathian presented a couple years ago, we look at this barycentric motion constraint. So the idea is we have the circle here that's the agent, we have the target position here, which is the square, and we have our relative position and our relative speed. And all we want to ensure is that the dot product of our relative speed and our relative position is negative, right? That means we always have to be approaching the reference position. So that's exactly what we do here. We define this constraint g, it's piecewise in the relative distance. If you're outside of some desired distance d, then we just have a function beta, that's a function of the state, plus the dot product of the relative position and distance should be less than or equal to 0. So if beta is positive, this will have to be negative, we'll approach the target. Once we get within a distance d of the target, then we just have the relative position should be less than or equal to d. So we're putting a disk of radius d centered on the target. We're forcing the agent to approach it and then remain within this disk. If the disk is very big, you might have a bunch of agents aggregating inside of it. If the disk is very small, you're going to basically drive the agent to a point. And using our previous analysis, there's a couple of useful properties that sort of pop out from this. So, for example, when we are initially sort of spiraling in with this negative dot product, at some point we'll cross into the disk. And at that transition, even though the constraint is this piecewise function, we can guarantee the control input is continuous because we're going from a constrained to an unconstrained arc. So that's a pretty useful property. We can also say that if beta is lower bounded by some positive number, then we will reach the disk in finite time. And finally, we can say once we've entered this disk, we will remain within it for all time. So this is a constraint that captures the agent and forces it into a closed disk in finite time. So, unfortunately, due to time constraints, I'm not going to be able to go over the extension to collision avoidance, although you can see that in the paper if you're interested, or definitely feel free to connect with me offline and we can discuss it more. The main thing, though, that we've talked about is this proof of continuity for the control input when a K integrator system with these states in Rn is transitioning between constrained and unconstrained arcs. We've got this barycentric motion constraint that has some useful properties. It's easy to use and drives agents into some desired reference position. And then for future work, we're really interested in extending this into differentially flat systems, where you take some nonlinear, complicated system and you're able to convert it into a bunch of integrators of different sizes. And also how we might generate multi agent trajectories with collision avoidance. So, thank you so much for your attention. I can take any questions now and, of course, offline throughout the rest of the conference. Thank you.